Hi there, welcome to Just Another Dev. And in this video, we are going to talk about the queue data structure in JavaScript. So we are going to implement the queue data structure using linked list in JavaScript, though it can be implemented using other data structures like object and array as well, but we are going to use linked list as we have used it in Stack. So before we go ahead and implement the queue data structure, let's understand what is a queue first. So queue is basically a first in, first out data structure, or basically called FIFO. FIFO basically means whatever is going to get inside the queue first is going to come out as well first, right? Which is basically the case with normal queues as well, right? So if you are in a queue and you are the first one in the queue, then you will be the first one to get out of the queue as well. Okay. So if we have elements like 6, 7, 8, 9, 10, 11 over here, and if 6 was added initially, then 6 will go out initially as well, right? Then 7 will come and then 7 will go out, then followed by 8, 9, 10, and 11. So that's how basically a queue works, right? So pretty much very straightforward, right? So whatever comes first is going to get out as well first. Yeah. And if we talk about the application of queue in computer science, so there are many applications for queue data structure, namely task scheduling. So basically, queues can be used to schedule tasks based on the priority, whatever the task is going to go first and all. And it is also used for things like event handling. So if you have a set of events which have to be executed in order, you can use a queue for that. The other example would be BFS algorithm. If you are aware of the breadth first search algorithm, then queue is used to implement that algo. Let's see how we can implement a queue using linked list. Okay, so we would need variables like size, the front, and the rear, right? So initially there won't be any element in the queue, so the front and rear will point to null, and the size initially will be 0. Now let's say we want to add some item to the queue, right? So let's say we are adding this 5. So what will happen? Our front and rear both will point to this 5. Front, rear, both are pointing to this 5 element in the queue. Okay. Now when we are going to add one more item, so what we can do, uh, we can add it after this 5. Okay. And as you know that in queue, whatever comes first has to go first, right? So whatever we are adding should add after 5 only, right? So if we are adding 6, it will come up here. Front is still not changed, and our rear will now point to this 6. Okay. Similarly, if we are adding 7, our front is not going to change, it will still point to 5, and the rear will now point to this 7. Now, if we talk about removing elements from the queue, so since it is a first in first out data structure, so our first element that came in was 5, right? Now, if we want to remove this 5 from the queue, we just need to change this reference or front from this 5 to 6, and we can break this thing. Okay, so what we'll do, we'll say uh, this front is going to point to this 6, and we are breaking this 5 to 6 link. So our new linked list becomes 6 and 7. This is our front and this is our rear now. Similarly, if you want to remove the next element, that is 6, it can be removed from here. This link can be broken, and now our front and rear are pointing to 7. Okay, so this is how we are going to implement queue using linked list. So let's see that in the code. So let's create a folder called queue. Inside queue, we are going to create a queue.js file. Okay. Now, as we saw that we are going to use linked list for our implementation. So I'll just import this linked list node. and let's call it node. Okay, and we are going to create our queue constructor function. It will have size equals 0. It will have front and rear pointing to null, as we already saw. Okay, so this is basically going to initialize our queue with size 0 and the front and rear pointing to the null. Now let's talk about the enqueue function, which is going to basically add item to the end of the queue. Okay, so queue dot prototype dot enqueue equals to this function, which is going to accept a value, and we are going to create a new node. Let's just call it node val. Okay, and if the queue is empty or this dot size equals to 0, then what we are going to do, we are going to say this dot front equals to node and this dot rear is also equals to this node. Otherwise, if it is not empty, then what we are going to do, we are going to basically change our rear, right? So this dot rear, which is currently pointing to the first node, let's say, right, or whatever node it is pointing to, what we have to do, we have to add this new node after that, and then the rear should point to that particular node, right? So this dot rear dot next equals to node, and this dot rear equals to node. So what we have done, the current rear that we have, the current last node, we have added a node after that. So this dot rear dot next equals to node, and now we are saying that the rear is going to point to this new node itself. Okay, I'll just show it with an example as well. So let's say we have 5 over here, both front and back are pointing to this 5. When we are going to add 5, so what we are saying, we created a new node 6. So this dot rear dot next equals to node. So 5 dot next, basically it is going to be 6. And now we are pointing this rear over here, 6. So this rear is pointing to the 6 now. So that's what we are doing here. Finally, we'll increase the size and let's just return the new size of this queue. Okay, now let's talk about dequeue. Basically, remove item from the front. So let's create this prototype function equals to function, and it won't accept any value because we just need to remove an item. So if the size is 0, then we need to return null because we don't have anything. Or if the size is 1, then basically our front and rear are pointing to the same node. Then what we can do, this dot front equals to null, this dot rear equals to null, because we need to remove that only element, right? So both front and rear will point to null now. And otherwise, if the size is greater than 1, right? So what has to happen? So let's take the same example again. So we had 5 and then 6, right? So since 5 came first, we have to remove the 5 only. So what will happen? The link from 5 to 6 should be broken and the front should point to 6. Okay. So this dot front should point to this dot front dot next. But before that, let's put this in a temp variable. Temp equals to this dot front. So what we are doing, we are putting this 5, the reference to this 5 in this temp variable, and then we are saying, okay, now this front will be pointing to this 6. Okay, and we can say temp dot next equals to null because we are breaking this link. 5 to 6 link we are breaking. So we have said temp dot next equals to null. Okay, and we can return the temp item, which is basically removed. Okay, so that's how we are going to dequeue. The other function that we can create is empty, which is going to, though it is not uh, completely required because we already have the size, but if you want to create, you can just make it like return this dot size equals to 0. One more thing over here, we'll have to reduce the size as well when we are doing a dequeue. Okay, and one more function that we can create is the peak, which is going to basically return the first element or the front element. Okay, and it is going to return, it is not going to remove, right? So we just, when we try to do a peak, it will just give us the element that is sitting in the front, right? It will not do any dequeue or anything over there, right? It won't remove it. So prototype dot peak equals to function, and it is going to return, if we have front, then it is going to return dot val, otherwise it is going to return null. Okay, so if we have some value in the front, it is going to return that, otherwise it is going to return null. So that's mostly about our queue data structure. Let's see if it is working properly or not. I'll just do a module.exports equals to queue here, and we can create our queue test. So let's just do a import of queue over here. So what I'm going to do, I'm going to create a new queue, and let's just do a queue.size in the beginning and see if it is going to work fine or not. I'll just do node queue queue-test.js, and it is returning a 0 in the beginning, which seems to be correct. Now let's add something to it. Enqueue, and I'm adding 5. Now I'm adding 6, and also let's see what is there in the front. So we are going to do a queue.peak, and let's run it. Oops, there is some error it is giving us. Let's see what is that. Okay, it's a named export, so that's why it is not allowing us this node. Let's just call it node. Okay, let's see if we can run it again. Okay, it gave us correct thing in the beginning, but this queue it is not returning us any value. Now why that should be? We did this q.enqueue5. Okay, if this dot size equals to 0, it should have created this new node and the size should have increased. And when we are doing this peek, it is checking if there is anything in the front, otherwise it is. Okay, so it is called value, that's why it is not giving us anything. It's not called val, so I'll just change it to value and it should work fine. Okay, so it is working fine. We added 5 and then we added 6, but since it's a FIFO queue, it's a FIFO data structure, our 5 will always remain in the front. Okay. Okay, now let's do this q.dq and see what happens. And we can just print it because it is returning us the element that is getting removed. So it should ideally remove this 5 first and then 6. Let's see what happens. Oops, sorry, I have to run it in terminal over here. Okay, we are getting some error. So I think it returned 5 initially. This is fine. And after that it was not able to return. It is saying this error over here. Okay, got it. So this code should ideally not be here. It should remain over here. So what we are doing in this case, if the size is 1, right, and we are dequeuing, then our front is basically going to point to null, right, because there is nothing else over there. But our rear still might be pointing to the same variable, right? The same element. For example, in this case, right, if we only have 5, our front and rear both are pointing to this 5 only. So for the front, we are removing it. But what about the rear? Rear is also pointing to this 5, right? So if the size is 1, we are saying that the rear is also going to be null because we have removed this element. So let's see. Let's try this again. Okay. So size was 0, we include 5, then this, we did a peak, so it is 5 only. Again, we added 6, again peak 5. And then if we are doing DQ, then it is giving us 5. And again, if we are doing this DQ, then 5 is already removed. Now 6 is in the front, so it is giving us this 6. Also, we can do a check on the size as well if size is empty, or we can just do a q dot is empty just to check that function as well. And it is giving us true. Basically, the queue has become empty because we have removed all the items. Okay, so the test cases are seem to be working fine, and this is mostly about the implementation of queue data structure. Now let's go ahead and see the time complexity of the queue data structure operations that we just did. So as we see here, whenever we are adding an additional node, we are not doing anything but just adding a few pointers, right? So we create this node and we just point it from here to here. Similarly, the same thing is happening over here, right? When we add this new node 7, we just added one pointer on this new node, right? So the time complexity for the enqueue operation is O of 1. It's a constant time complexity. We are not doing any operations which are going to take a lot of time, right? It's a constant time complexity for the enqueue operation. Similarly, when we are doing a dequeue, again we are just removing some references. So for DQ as well, the time complexity is O of 1. Same thing for the peak because we already have the reference to our front element. So this is also going to be O of 1. And the space complexity is also going to be constant time, which is O of 1 because we don't need any additional space when we are adding more inputs, right? When we are adding more items or removing items from this. Okay. The time and space complexity comes out to be O of 1 for Q when implemented using linked list. So that's about it. Thanks for watching. Do like and subscribe if you like the video. Thank you.